Hey everybody, so welcome. This is going to be Monday's video. I hope you had a restful weekend and are excited to get back into doing math. Anyway, so now our class is going to diverge into talking about the symmetry of a function. We're now describing a function's symmetry. So in this class, when talking about the symmetry of a function, we're asking the question, is the function even? Is it an even function? Is it an odd function? Or is it neither? All right? So functions that are even satisfy a particular condition. All right? And that condition, which we talked about in class briefly the other day, is this. All right? Even functions must satisfy this condition. And we'll get into it more later in this video. What about odd functions? Odd functions have a condition they satisfy. Here. So basically, just a quick interpretation of these equations. So for the even function, we see that if we multiply our x values by -1, our function will still have the same y values it had previously. All right, and don't worry, we will get into it. Here, if we multiply our functions for odd functions, if we multiply our functions, our x values, let me say that properly. If we multiply our function's x values by -1 here, what we get is a function that has undone the multiplication by -1. Like we see that on its x values, we see the minus go away here. But our y values become negative. That's kind of crazy, you know? So don't worry, we'll talk a lot about this. This will be a rather long video, so brace yourselves. How do I check whether my function is even or odd? Or neither, all right? I'm going to just erase these. Oops. Or neither. Well, two ways, guys. Two ways. Number one, graphically. All right? Graphically, so this is basically a graph on a coordinate system. All right? And then we can also check the symmetry of a function. If we don't have the graph, we can check it analytically. This is a word you guys are probably encountering for the first time, or maybe you already encountered it, I don't know. But analytically meaning using a particular function's formula. All right? And we'll see both examples in our practice. All right? Awesome. Anyway, so what does it mean to be an even function graphically, you know? So what does that mean? All right? That's a very good question to ask. All right? So I'm going to put the condition of our even function here. So the condition for our even function. So condition for even function. F of x will be equal to minus f of x. All right, look, Here we have a function of this which has this formula. All right. So this is what this function looks like. Don't worry, you don't need to know what it looked like yet. But for now, just believe what I say. So most of you know this is a parabola. And I'm telling you that it's an even function. So when I have a graph like this, of this sort, in this manner, on my coordinate system, and this is my, of course, my y, and this is my x. If I rotate my function by 180 degrees, okay? Remember the example we had in class. If I rotate my function by 180 degrees across this line, across the y-axis, all right? Think about the y-axis as a long stick, and my function is just right on that stick. Then if I rotate it 180 degrees, I turn my function 180 degrees, all right? So let's say here it is. If I turn it 90, it's going to just be, we're going to see a line. It'll just be dark, like a straight line, because I'm turning it. I mean, I'm looking at it from atop, like, yeah. And then if I turn it 90, I'll see a straight line only. And if I turn it another 90 degrees to make it 180, I'll see the same function, which is pretty insane. All right. So what's going on here? Let's look at our condition. So we said that if we have an even function and we negate our x values, we multiply our x values by -1, we will basically have the same, the function will basically have the same range. Now let's see if this is true. How will we do this? We're going to use tables. All right? We're going to have a table of our x values, a table of our y values, or if you like, f of x values. And then we're going to have a table of our minus x values and of our minus f of x values. All right? So we need some numbers to work with. I'll just pick a few from this from our function here. So here this point is 2. I look at the x-axis first. 1, 2. This point is 1, 1. This point here is 0, 0. This point here is -1, 1. I hope at this point in the course, you guys can see how I'm doing this. All right. Anyway, so yeah. Actually made a small mistake here. This point here is actually, let's see. Okay, just take the point as it is. Don't worry about how I found it. 1.42. All right. Because you see here, if I go from 1 to the next line, it's going to be 0.2. I add a 0.2 again, 0.2 is going to be 4. So that's 1.42, all right? Just according to the scaling factor. And then here, this will be minus 1.42. Yeah. So what are our x values here? Just list the x values. You list the x values, you got 1.4, 1, you got 0, and then we also got -1 and -1.4. Okay, so now let us write the y values for our points. We have 2, we got 1, we got 0, and then we got 1 again, and then we got 2 again. All right? This makes sense for the points that we have. So now let's multiply all our x values by -1. So it's going to be minus 1.4 minus 1, 0, and then 1, 2. You see, I'm just getting these values here, and then multiplying them by -1. So how do we find the outputs now? How do we find our y values? So we have to go to the particular point on the x-axis and see what it touches for y on our y-axis. So let me go to -1.4. So -1, and then we have, this is -1.2. It's going to be -1.4. What does my -1.4 function touch? So if I go up, oh, it touches 2. Wow. That's the same as here. If I go to -1, it touches 1. -1 right here, it touches 1. If I go to 0, it's still 0. If I go to 1 again, +1, I get 1. If I go to 2, x equals 2. Sorry, if I go to minus x, what? Sorry. If I go to, this is a mistake. This x here is supposed to be +1.4. If I go to +1.4, I get 2. So what? Do we see this? Do we see this, guys? F of x is equal to minus f of x on our table because the values on the tables are exactly the same. They're exactly the same. Pretty cool, guys. Pretty cool. Pretty cool. So what about analytically? Let's try to solve this. All right. Let me show you how you can do this algebraically. So again, we have our function x to the 2. Let's put in our condition. Our condition is f of x is equal to minus x. So yeah, this is our condition for even functions. All right. So what's f of x? F of x is equal to x squared. All right. So f of x here is equal to x squared. So basically, actually, let me restart this. Let's start by solving our right-hand side. Right-hand side. All right. So our right-hand side is over here. This is the right-hand side. In fact, I'll put them in different colors. All right. So our right-hand side, let's solve for right-hand side. F of x is equal to x squared. All right. So that's our right-hand side. Now let's try to solve for our left-hand side. All right. Our left-hand side, it's going to be f of x is equal to x squared. But now we need to multiply it by -1. So minus f of x will be equal to minus x squared. But minus x squared is just x squared. So our right-hand side equals our left-hand side. So x squared is equals x squared. Let me put this back in blue. X squared is equal to x squared. Wow. Wow. we just proved that x squared is an even function. Nice. All right. Let's talk about odd. All right. Anyway, let's talk about odd functions. So, what does it mean to be? I kind of felt a bit lazy here, it seems. What does it mean to be graphically odd? All right. So, for the odd function, the test to see it graphically is different from the even function. For the odd function, let's see, before I talk about conditions and everything, graphically, so to test if it is odd, comma, 1, the function needs to be the same if I rotate the origin 180 degrees. All right. So do we know the origin? The origin is right here. That's the 0, 0. That's the origin. So now I'm telling you, to see if a function is odd graphically, we need to rotate the whole origin. We need to rotate the whole coordinate system by 180 degrees. And it should be the same function. All right? So look, I have an iPad here. So I'm fortunate enough to just be able to get this. Can I select this? And then can I rotate it? Boom. So look at the previous photo of our function. Right now we're like this. All right? Just for clarity, before rotation. All right, this is just a sketch. And then after I rotate it, 180. Boom. After rotation. Well, we still have the same function. I know my sketches are very bad, but I hope you see it. If we rotate the whole coordinate plane, all right, we basically have the same function. All right? All right, I hope you find that cool. Okay, so now let's again remember for conditions, when it comes to condition for odd function. The conditions are basically what the function needs to satisfy for us to call it odd. All right, those are the conditions. So our condition is if we minus our x values of our function, we expect the y values of the function to be minused and the x values to be unminused. I don't know if that's a correct word, but we see the x here is not negative, but the x here is negative. So the x values lose the negative, and then the y values get the negative. All right? So, again, I'm going to get some points. Let's see. I'm just going to get points on the graph. We've done this before in class several times. If you're confused on how I'm getting the points in the graph, come see me in my Highland Nation hours, please. Okay, that's 2, 8. I'm only gonna do the ones in blue. Let me just put some confusion here, yeah? 2, 8. And then this is 1. Up 1. Alright, and this is -1, and that's -1. Alright, so that's 1, and we got -1, then we got -2 and 8 as well. Alright, so this point is 1, -1. This point here is -1, -1. And this point here is -2 and -8. So yeah. So let's make another table. We have f of x. Yeah, f of x, our regular f of x values. Actually, let me say, instead of f of x, I'll begin with x. All right. Then we're going to get f of x right here. All right. And then we'll say minus x right here. And we'll give it some minus f of x. All right. Nice. So what are our x values? Just our regular x values. We got 2, we got 2, we got 1, as well as -1, as well, and then -2. So this is just some values I selected, but because it's a function, they should behave as the whole function would behave. It's basically showing us how the whole function represents. So now those are x values. Now let's get the y values associated with those x values. 8 -1 -1. Then we have, mistake. I'm doing this at 10 p.m. guys, forgive me, all right? It's 10 p.m. on a Saturday night. All right, so we have, so this x here just becomes 1. This x is 1, yeah? And then this over here becomes a +1, yes. And then my f of x for -2, let's hang on. Sorry guys, too many mistakes. Hope it's not confusing you. Please come see my office hours. I'm just trying to figure out the correct x and y axes, all right? So we have -1 and the -1, the correct x and y numbers. And then we have a -2 and the -8. All right, these are the correct pairings. This is what we have: 2, 8, 1, 1, -1, -1, -2, -8. All right. So now let's see what happens when we make our x's negative, or we multiply our x's by -1. So we get -2, -1. So I'm multiplying these guys by -1. So then we get 1, then we get 2. All right. So now, what all functions tell us that if we minus our x values, we will get a positive range, so a positive set of y values for our function, or sort of x values. So when we minus our x values, we get a positive set of y values for our function that will multiply by -1. All right. So First, let's get the positive y values. All right. Actually, instead, let me rephrase this. So basically, when you say minus f of x, to find our negative f of x, we're going to go to our graph and just try to find them. All right. What we expect is these values, these f of x values, we expect them to be negative just by finding them. All right, just by finding them. So if I go to x negative 2, I find, so that x negative 2 is over here, I find negative 8. Oh wow, I just found it. If I go x is negative 1, x negative 1 here, oh wow, see, just found it. Wow. If I go find x1 over here, oh, my former one was negative 1, but now it's just 1. And then if I go find x2, I find positive 8, where previously I found negative 8. And boom, our condition is satisfied. Okay? Because f of minus x is equal to minus f of x. Boom. All right. Great job. So now, let's calculate. All right. Let's do this analytically. Let us try to do this analytically. Let's try to prove it to math. Let's do math. Although we're doing math there, but we're mostly listing graphically. But now let's try to use some formulas. So what's f of minus x? You know, what's this? This is basically minus x over 3, to the power 3. So you take minus x, and you take the exponent, and you're gonna get minus x over 3. You know, so it's basically minus x, minus x, minus x. Hang on. All right, then negative plus negative is positive. I have a positive, and another negative again. That's going to be x to the third. All right, so we figured out that minus x minus f of x is x to the third, and this is our left hand side. So left hand side. Now let's see if we can make our right hand side equal that. All right. Oh, I forgot my minus signs. Yeah, let's see if we can make our right hand side, which I will give a different color. To make our right hand sides equal this. So my right hand side is minus f of x. It's going to be equal to, so what's f of x basically? Positive f of x, or since f of x is equal to 3, minus f of x would just be 0 x to the 3, sorry. Minus f of x would just be f minus x to the cube. So, yeah, that's basically how this video has been a summary of how we would both use mathematics, algebraic formulas, and use a graphical method to determine the symmetry of a function. And if a function is still like if a function does not satisfy any of these factors, it's neither. All right, so it's neither even or odd. So in summary, right, even functions satisfy the condition f of minus x is equal to f of x. And then odd functions satisfy the condition f of minus x is going to be equal to f of x minus f of x. All right? If a function does not satisfy these, comma, then it is odd. We are not done with this video. We are not done. All right? We are not done. We have another chapter to go with, another chapter to go for. We have a lot of stuff to do. We're a bit behind the other class. So stay with me. All right? I want to take a break, drink some water, and then come back. Okay? But this video is not done. Okay? So, we're going to move on to linear functions. All right? So, a linear function is a type of function. All right? Even functions and odd functions are not types of functions. Those are just descriptions of the symmetry of functions. All right? Okay. So, I'm just going to write that here because I don't want to be confused. Linear functions are a particular type of function. All right? Even and odd functions are descriptions of a function's symmetry. All right? All right, awesome. Anyway, so before we go into our section of linear functions, I would like to go over a few definitions, all right? Just to make sure we're on the same page. You probably already did this in Algebra 1, but I think a review of these would be good, okay? So, and I'll try to be as fast as possible. What's a variable? This is a letter, all right? That stands for a number we don't know yet. All right. So, if I go number one, I want to connect an example of this. It would be, let's say, if we have 2x plus 3 here, comma, here, x is the variable. We don't know what x is, all right? We don't know what x is, so x is the variable. And number 2, the coefficient. So, this is a number in front of a variable. All right? So this number is always in front of a variable. All right? Example, 2x. Here, 2 is the variable. Sorry, 2 is not the variable. 2 is the coefficient. All right? What about x? Think about this. What about x? What is its coefficient? Think about that one. All right? It should be in the after post lab quiz, post video quiz. And a constant. So a constant, this this is a number by itself with no variable. All right, so that's what a constant is. A number by itself with no variable. All right, so an example you'd like, probably. So if I have 2x plus 3, comma, here 3 is the constant. Nice. All right. See, 4, an expression. So what is an expression? So this is a math phrase. It's a math phrase, all right? Made up of numbers, variables, and operations. All right? Although, an important feature of this is there's no equal sign in an expression, all right? So, for example, here if you just put 2x plus 3, this is an expression. All right? If I say 2x plus 3 equals 4, that is not an expression. That is an equation because of the equal signs. All about equal signs, all right? Like terms. So these are terms. These are terms that have the same variable raised to the same power, all right? These are terms that have the same variable raised to the same power. Yeah. And order of operations. Oh, sorry. Let me give you an example. So I'm trying to rush through this as well. So if you have color, if you have 2x plus 3x, they're like terms. You can add like terms, equals to 5x. But if you have 2x plus 5x squared, these are not like terms, all right? Because of the x squared. They have to be the same variable and the same power for them to be like terms, all right? And then order of operations, okay. PEMDAS, all right? This is basically a description of how you should solve math problems, all right? So you start by your parentheses, exponents, then you do the any multiplication you need to do, multiplication or division, if you like. And then after you've done those 4 in order, you do any addition / subtraction. All right, awesome. We're almost done, guys. So anyway, what is a linear function? All right, what is the linear function? What is this? Let me try to change the color to keep it interesting for you guys. Yellow is a horrible color. I want a color that you can see clearly. What is a linear function anyway? A function of the form y equals mx plus b. All right? Here, x is our variable. B is our constant. It's a constant. B is a constant. All right? M is also a constant. This is a constant. All right? These two have an existing value. So M is a constant because it's the slope. It's the slope. It's the slope. And B is our constant because it's the y-intercept. All right? So we know these. We can get these from a graph. All right? And I say y equals mx plus b, but really, if we wanted to, we could say f of x is equal to mx plus b. So anything, so this is correct as well. Any function that has this form, is a linear function. All right, so things to notice, all right? So a summary of linear functions, then we're done, all right? I'm tired, I want to go to bed. You see, it's 10:56 p.m. on a Saturday night. I'm doing this for all of you guys. All right, because I love you guys. Anyway, a summary. So linear functions are of the form y equals mx plus b. And by the way, just for clarification, linear functions are lines. All right, they are lines. Okay, they are lines. All right, they are lines on the graph. All right, if we have a Cartesian plane, they are lines. And the good thing about lines is that the math is easy. All right, or at least it's easier than when it's not a line. A main reason it's easier is that a linear function variable will never have an exponent greater than 1. All right? So you see, look, we have y equals mx plus b. If I say that if I square my variable, x squared, this is no longer a linear line. It's something else. But we're focusing on linear lines. All right? Anyway, I hope you had a good time with this video. Have a good night wherever you are. I think this is the neon night. So, yeah, and yeah. See you in class. Bye.